So ఈరోజు we'll discuss about pumps. Pumps are devices which can increase the energy of fluid, which add energy to fluid. So they can add which means hello Praneeth, which means they can either increase the pressure, increase the elevation, or increase the velocity of the fluid, or all three. So there are two broad classification of pump: reciprocating and rotary pumps. In the reciprocating pumps, they have a fixed they have a fixed outer casing, and they work by varying the volume. So initially, when during the intake stroke for a reciprocating pump, the piston moves back. So the piston moves in this direction. When the piston moves in this direction, we achieve this. So this is the piston, and the fluid flows into the inlet valve, and the outlet valve is closed. And for the outlet stroke, once this entire region is filled with fluid, we close the inlet valve and the piston is pushed with the outlet valve open. This causes the piston is now in this at this position. So all the fluid moves out. So this is how a reciprocating. Hello, Sarika. So this is how a reciprocating pump works. So the piston is reciprocating within the volume. So you can see that the volume occupied by the fluid is continuously changing in a reciprocating pump. Coming to a rotary pump. A best example of the rotary pump is our centrifugal pump, where we have an inlet and an outlet, and we have a rotor. So fluid enters. Because of the spinning rotor, the energy of the fluid will be increased and it is sent out. So you can see here the volume is remaining constant, whereas the energy is being added because of the motion of the rotor. So this rotatory motion, because of this rotatory motion, they are called as rotary pumps, and reciprocating pumps. Now, let us focus in detail about centrifugal pumps. So for centrifugal pumps, there are few important points which are to be remembered. So centrifugal pumps, basically we define the RPM. RPM is nothing but it is denoted by N. It is the number of revolutions per minute, of rotations per minute of the impeller. So the impeller is located inside a casing, and then you have the outlet. So for a given fluid, we need to know how the flow rate, how the head, and how the pressure. How are these three things related to the RPM at which the pump is operating? So it is observed that. Hello, Prarthana. It is observed that Q is proportional to N, H is proportional to N square, and P is proportional to NQ. So which means if you are delivering 100 liters per minute by operating at 2000 RPM, or by operating at 2000 RPM, if you want to deliver 200 liters per minute, you need to operate at 4000 RPM, because the flow rate Q, which is also known as the capacity, varies linearly with the speed of rotation N. And for example, head. So what is the head developed in a centrifugal pump? In a centrifugal pump, the head developed. So if you look at the Bernoulli's equation, you have P by rho plus V square by 2 plus GZ1 plus eta WP is equal to P2 P1 V1 GZ1 P2 by rho plus V2 square by 2 plus GZ2. So this is known as the pump head. So pump head is nothing but this this entire quantity minus this quantity. So how does the head vary? So the head developed varies with n square and p power. That is the total power consumption. It varies with n cube. So for example, if you're operating, at 2000 RPM and the power consumption is, let us say, 1 kilowatt or 2 kilowatt. If you increase the RPM to 8000 RPM, can you tell me how the power is going to vary? Or if you make it 4000 RPM, how many kilowatts of power would be consumed? So it is going to be 4000 by 2000 to the power 3. So it is going to vary as 2 cube. 2 cube into 8, which is 16 kilowatt. This is going to be the power required. So you need to remember these. These are known as the pump scaling laws. So in order to remember this, you can use a sentence. So very hard problems are as easy as 1, 2, 3. So VHP. V stands for volumetric flow rate, which varies as n power 1. H stands for head, which varies as n square. P stands for power, which varies as n cube. So by remembering this sentence, you will be able to remember the pump scaling laws easily. By the way, I found this from Senjal book. Senjal Simbala.
Wow.
Fluid Mechanics
Thank
by,
you.
okay, by Senjal Simbala. Okay. Now let us look at some more pump curves, which are called characteristic curves. So characteristic curves of a pump, they are, so you plot delta H, that is the head developed, power requirement, and efficiency. When you plot all these three against the volumetric flow rate Q, they are known as the characteristic curves. Let us see how the head is going to vary. So when you plot head on the y-axis and flow rate on the x-axis, theoretically, that is in an ideal pump where you're neglecting any frictional losses, you have this kind of decrease, a linear decrease in the head. But in reality, the head decrease is going to be sharp. And at this point, the head will become zero. So this is known as zero head flow rate. Similarly, if you operate at the highest possible head, largest head difference, your flow rate is going to be zero. This is a shut-off flow rate. Shut-off head, sorry. This value of head is known as the shut-off head, which means you won't have any flow. The flow rate is zero. And when flow rate goes to a maximum, you won't have any head. So it is a zero head flow rate. This is the first diagram. And the second diagram is going to be for the power consumption against flow rate. And there is a reason why this does not follow a linear path like the ideal case, because during the derivation of the ideal head for a centrifugal pump, one of the assumptions we make is that the flow is there is no circulatory flow, which means, so if you have a centrifugal pump and this is the inlet of the pump, let us say a fluid particle enters the pump, it immediately acquires the velocity, higher velocity or higher pressure, and it is going to exit the pump. But in reality, it is highly possible that a fluid particle which enters the centrifugal pump is going to circulate around in the pump for some time and then leave the pump. So this is kind of like a mixed flow reactor, where the ideal case you are saying, where you don't exactly know how much time a particle is going to spend inside the pump. So it may leave instantaneously or it can undergo circulation for certain time. And whenever it is undergoing circulations, it leads to loss in head. As a result, we have a steep decrease in this is the actual curve, and this is the ideal case. Now let us look at power. So the power, we know that if you want to pump higher flow rate, you'll require more power. So the power is going to increase. And there is something called, this is the total, there are I'll sketch two powers. This first power is the total power. And this is the power delivered to the fluid. So what is the difference between these two? The difference between these two is the power which is lost in overcoming this circulation and friction. So if you are inputting 100 kilowatts of power, let us say 20 kilowatts were lost because of this friction and circulatory flow, the remaining power is going to be just 80 kilowatt. So these two curves represent 180. And then let us look at efficiency curve. Efficiency against flow rate. So for an ideal situation, you will have a 100% efficiency line, whereas in an actual pump, the efficiency initially increases and then it slightly decreases. Initially, it increases steeply, the efficiency, and then there is a slight decrease. So these three are the characteristic curves of a pump. Now let us look. So any questions so far on centrifugal pumps? Okay, actually I'll show you the McCabe and Smith, where they developed the equations. So yes, this is the theory of centrifugal pump. So in the centrifugal pump theory, they do a detailed vector fluid mechanics analysis of a blade. So this is a blade inside the centrifugal pump, and they divide the velocity into velocity components along the blade and velocity components perpendicular to the blade. And after doing some analysis, we get this relation that yeah, work done per unit mass of liquid flowing through the ideal pump. This is the head work relation in an ideal pump. So you can just go through this derivation, but it is not very important from a gate perspective. But it will help you get a better understanding of why we got the scaling laws as Q proportional to N, H proportional to N square, and P proportional to N cube. So all these things are derived from that theory. And you can also look at the diagrams of the pump and watch YouTube videos to learn more about pumps, because these are going to be very important from an interview point of view. Now let us look at a problem. So let me know once you have read the problem.
Yes or no?
Okay, let us look how we can solve this. So the pump head versus flow rate is given as H is equal to alpha minus beta Q, where alpha and beta are constants. Obtain an expression for the pressure drop in the pipe in terms of volumetric flow rate Q. So whenever you have a problem on pump, it will be mostly related to the Bernoulli equation. So writing down the Bernoulli's equation, we have P1 by rho plus V1 square by 2 plus GZ1 plus WP or eta WP is equal to P2 by rho plus V2 square by 2 plus GZ2. Now, usually in case of pump, the elevation, so this is the inlet and this is the outlet. If I consider this to be Z1 and this to be Z2, Z1 and Z2 are almost the same. There is not much elevation gain at the inlet and the exit of the pump. So you can neglect these terms. And also usually the velocity of the fluid will remain the same for liquids, and the pressure is going to increase. So you can also neglect the velocity terms, because if you do a continuity analysis, that is for an incompressible fluid, if the diameter of the pipe here is d and the diameter of the outlet pipe is also d, we know that v1 a1 should be equal to v2 a2, but a1 is equal to a2, so v1 should be equal to v2. So essentially you have this equation, and now in order to convert this equation into head, we need to divide by rho g. So if you divide it by g, you have uh, P1, oh, sorry, P, P2 minus P1 by rho g is equal to eta WP by g. Eta WP by g is given as the head developed, which is alpha minus beta q. Alpha minus beta q. There is also one more thing which we need to consider. So it is a flow in a the flow in the pipe is laminar with a fanning friction factor. So we should also include the friction term, which we did not do here. So they have given the fanning friction factor to be F is equal to A by Reynolds number. And so let us include that as well. So it is going to be, the friction factor is going to be 4F L by D into V square by 2G. So once you include that, and we know that V is equal to Q divided by, which is the volumetric flow rate divided by pi by 4 times D square. D is given in the problem. So D and L are acceptable variables, but V is not given in the problem. So we replace V with this term, and F. We replace F with this term. F is equal to A by RE. So if you do that, you're going to get 4 A by RE. So Reynolds number is rho VD by mu. So rho VD by mu. The V will get cancelled with one of this V. We have rho D times mu times V. Instead of V, I'm substituting this. Q divided by pi by 4 D square into G. So let me know if I'm making any mistake in the calculation. Please check it. This is 16 A mu Q by, oh, I missed an L. 4F L by D. There should be an L. Rho pi G D power 4 into L. So D power 4, L is in the numerator. Is this okay? Did everyone get the same thing? Okay. So,
Yes, Anna.
okay. We can go ahead then. So we have P2 minus P1 is equal by rho G is equal to alpha minus beta Q. Plus we also need to add this, sorry, subtract this friction term. 16 A mu Q L by rho G pi D power 4. So this is delta P by rho G. So what is that they're asking in the question? They're asking us to find out, obtain an expression for pressure drop in terms of Q. So we have the expression. Delta P is equal to rho G multiplied by alpha minus beta Q minus 16 A mu Q L by rho G pi D power 4. This is our expression for delta P. Is it clear to everyone, the procedure so far? So it is entirely based on the Bernoulli equation. And then let us look at the second part of the question.
అన్నయ్య అక్కడ 2 వస్తుంది అనుకుంటా అన్నయ్య డినామినేటర్లో.
ఎక్కడ శివాని? ఇక్కడ
V² by 2G 4F L by D
Oh, right.
V²
Yeah,
by.
V square by 2G. Yes. థ్యాంక్ యూ శివాని. 2 తీసుకోలేదు. సో ఇది 8 అవుతుంది కదా? ఓకే. సో ఇది 8 అవుతుంది. రైట్. Let's look at the second part. Obtain an expression for steady operating flow rate. Assuming the only pressure loss in the system is due to the pipe flow. So they are asking us to obtain an expression for flow rate. Assuming that the only pressure loss in the system is due to pipe flow. Okay. So we can extend the same problem right from here. What they're essentially meaning is, so we have some pressure loss in the pipe. What is the flow rate that is required to exactly overcome this pressure loss? That is the question they are asking. So the head developed by pump should be equal to head losses, which means delta P is going to be 0. That is, you're not generating any extra pressure. You're only generating sufficient pressure to overcome these friction losses. So in that case, delta P is going to be 0. And so then you have alpha minus beta Q minus 8a mu QL by rho g pi d power 4 is 0. And once you isolate Q, you have Q is equal to alpha divided by beta plus 8a mu L divided by rho g pi d power 4. Is everyone clear with this concept? Why did I take delta P to be 0?
Yes, Anna.
Okay. So that's it. This is the problem. So the problems on Bernoulli's equation, which involve pump, which involve losses, make sure to practice them several times because they are problems which you should be scoring. They are easy to score and they are very predictable.
Okay, Anna.
So with that, we are essentially done with fluid mechanics. There are few problems. Since we have some time, let us try to solve these problems. Okay. Would you like to try this problem? Yeah, go ahead and try this problem. Take 4 minutes. Okay. So can anyone tell me how they did it? Any answers? This is the classic Bernoulli equation problem. So we have a nozzle which is exiting to the atmosphere. You take this to be point 1 and this to be point 2 and write the Bernoulli equation. We're going to have P1 by rho plus V1 square by 2 plus GZ1 plus, there is no pump, so I need not include the pump relation, is equal to P2 by rho plus V2 square by 2 plus GZ2 plus I also need to include the losses. Okay, let the losses be HF. HF is the term for the losses. But they have mentioned that the frictional losses between location 1 and location 2 is 10,000 pascals. So delta P is given, delta P loss is given to be 10,000 Pascal. Now we want to convert this into the loss per unit mass of fluid flowing. So in order to do that, we need to first divide it by the mass flow rate. Do we know the mass flow rate? I'm sorry, we need to divide it by density, delta P by rho. Delta P by rho. So we know the density is, or we can just replace delta HF by delta P loss by rho. And now we can go ahead and solve it. We know that because they are at the same elevation, GZ1, GZ2, you can ignore them. And you know, we don't know P1, but we know P2 to be atmospheric pressure. So you'll have PA minus P1 by rho. PA minus P1 is nothing but the PG, gauge pressure. That is what exactly they're asking. They're asking us the gauge pressure, not the absolute pressure. So PA minus P1 plus PA minus P1 by rho plus V2 square by 2 minus V1 square by 2 plus delta P losses by rho. Delta P loss by rho is equal to 0. But we know delta P loss given us 10,000 pascals. We know density. And we need values of V2 and V1. And it has been given that V2 is 16 meter per second. And but they also mentioned that D1 is equal to 4D2, which means A1 will be equal to 16 times A2. If A1 is 16 times A2, then V1 is going to be 1 by 16 times V2. But we know V2 is given as 16. So V1 is going to be 1. So we know V1 as 1 meter per second. And we know the density. So we can solve this equation to calculate this term, which is the gauge pressure. Is the problem clear to everyone?
Yes, Anna.
Okay. So always remember there can be multiple forms of the Bernoulli equation. You can write it as, so you can write it as P1 by rho g, Sometimes you can write it as P1 plus V1 square by 2G plus Z. Sometimes you can write it as P1 by rho plus V1 square by 2 plus GZ. Or you can just write it as P1 plus rho V1 square by 2 plus rho GZ. All these forms are equivalent. So this form P1 by rho G, this form has a dimensions of length. So it is also known as the head. Whereas this form it has a dimensions of, I think, yeah, it has a dimensions of energy per unit mass. And this one is in between both of them, where you are, so if you can see, the difference between them comes from the rho g term. So you have rho g here, you only have rho here, and you have nothing over here. Because multiplying with rho g is going to make the difference between these forms. And remember one form, and no matter what problem is given to you, I would suggest to start from that form, and just based on the data given in the question, you can convert it into either this form or this form by multiplying it with rho g.
Okay, Anna.
Let us see if there are any more problems. Let us look at this problem. I hope everybody is done with. So everybody, transport phenomena జరుగుతుంది కదా మీకు ఇప్పుడు right now?
Yes, Anna.
Okay then. So this will help you. There is something called the Navier-Stokes equation in fluid mechanics. So differential balance. Differential balance equations. Differential balance equations. Below you have again three. You have mass, you have momentum, and you have energy. And momentum lo you have three. You have x component, y component, or z component. So the mass, the differential balance equation for mass is going to be dou rho by dou t plus del times rho v is equal to 0. This is going to be the differential balance equation for mass. Similarly, and you obtain this results to the continuity equation. So the continuity equation, which we write it as rho v1 a1 is equal to rho v2 a2. This is nothing but a special case of this applied to a macroscopic system. So similarly, when you do a momentum balance, you're going to get a special class of equation called Navier-Stokes equation. So you're going to have So this is your Navier-Stokes equation for the x direction. Let us analyze this equation and understand what this equation, each term of this equation means. So dou by dou t of rho vx. So remember, this is a Navier-Stokes equation in the x momentum, for the x momentum only. I'm sorry, there is a rho over here. Rho ux. So this term represents rate of momentum generation. Rate of momentum generation. Or this can also be visualized as the unsteady term because you have a time derivative. And coming to this term is the convective term, convective transport of momentum, which means the momentum which is transported because of the bulk flow of the fluid. See, you can see here you have ux, uy, uz, which are the velocity components of the bulk fluid. So this is the momentum which is being transported by the bulk of the fluid. And then you have something minus dou p by dou x. This is the momentum due to pressure forces. So we know that whenever there is a pressure gradient, the fluid will tend to flow. And this term represents that pressure gradient. And then you have this term, mu times dou square u by dou x square plus dou square u by dou y square, dou square u by dou z square. This is nothing but the viscous term, or it is also known as the diffusive term, diffusive momentum term. Why is this called the diffusive momentum term? It is because it occurs, this represents the momentum which is occurring due to momentum transfer, which is occurring due to molecular diffusion. Like mass, if you assume like mass diffuses, you're also seeing that momentum can diffuse because of molecular motion. And that is taken care of by this term. And then you have rho bx. Rho bx is nothing but the momentum change due to external forces. So in this way, you are going to have Navier-Stokes equation for the x momentum, y momentum, and z momentum. And usually these lengthy equations for any particular system, after making certain reasonable approximations, you can boil them down to a very simple equation which can be analytically solved. For example, let us take hydrostatics. Let us take hydrostatics. In case of hydrostatics, we know that pressure Pa minus Pb is equal to rho gh. This equation comes straight from the Navier-Stokes equation. So let us see how we can arrive at that. Now I have a tank which is there is no motion, that is hydrostatic. And so there is no motion, there is no flow at all. So ux is 0. If ux is 0, can you tell me which ux, uy, uz are 0? Can you tell me which terms of this equation will become 0 now? And I'm writing the momentum in the y direction. So in the y direction, so this becomes dou p by dou y, and this becomes rho by, and all this become uy, 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 uy. So that uy is 0. Because uy is 0, ux is 0, and uz is 0, the fluid is stationary. This term will become 0. This term, all these terms will become 0. Even all these terms will become 0. All you are left with right now is minus dou p by dou y plus rho by is equal to 0. But by in terms of gravity, is nothing but the gravitational force. By is the gravitational force per unit mass, which is mg by m. So this by term is going to be nothing but g, because negative g, because it is in the downward direction. Now you have minus dou p by dou y is equal to rho g. This is nothing but your condition for hydrostatics. And if you integrate this, you're going to get PA minus PB is equal to rho gy, which is the same equation. So every equation you see can be derived right from the Navier-Stokes equation. So Navier-Stokes equation is a differential momentum balance equation, which is, so in order to arrive at this Navier-Stokes equation, you essentially start with a force balance. And after making a force balance, you make several approximations. They include the fluid is a Newtonian fluid, and the fluid is a Stokesian fluid. And yeah, these are the main assumptions which you make to arrive at this Navier-Stokes equation. Let us now look at the problem. So this is the problem where they are saying, so look at this, after assuming laminar flow, one-dimensional, fully developed, the y Navier-Stokes equation reduces to this thing. Mu d square vy by dx square plus rho g is equal to 0, where vy is the velocity in the y direction, mu is the viscosity. So the first thing they're asking is state the boundary conditions. So in order to solve any differential equation, you require boundary conditions. They're asking us to state the boundary condition. So this is the wall. This is the solid wall. And this is the liquid. And this is air. And we have fluid flowing in this direction. And the thickness is A. Sorry, the thickness is delta. So this is X and this is Y. Let us say, so this is X is equal to 0 and this plane is X equal to delta. Can you tell me the boundary conditions, anyone? At X is equal to 0, what should be the value of Vy? Anyone? So whenever there is a wall and fluid is flowing adjacent over the wall, what is the velocity of the fluid at this point, at the surface of the wall?
Zero.
The velocity is going to be 0, right? Because of the no slip boundary condition. So no slip boundary condition, which means at x equal to 0, Vy should be equal to 0. And at x is equal to delta, can you guess what might be the boundary condition?
A by T. అంతే అన్నయ్య.
X equal to, అంటే ఈ ఇంటర్ఫేస్ ఉంది కదా, లిక్విడ్ ఎయిర్ ఇంటర్ఫేస్ ఉంది కదా, వాట్ ఈస్ గోయింగ్ టు బి ద బౌండరీ కండిషన్ దేర్? ఓకే, లెట్ us look at it this way. సో అసలు ఇక్కడ వెలాసిటీ 0 ఎందుకు అవుతుంది వాల్ ఉంటే? వెలాసిటీని, సో ఫ్లూయిడ్ని అపోజ్ చేసే ఫోర్స్ ఏదో ఉంది, విచ్ ఈస్ కాల్డ్ వాల్ షియర్ స్ట్రెస్. వాల్ షియర్ స్ట్రెస్ ఉంది ఇక్కడ. ఆ వాల్ షియర్ స్ట్రెస్ వల్ల వెలాసిటీ అనేది 0కి వెళ్ళాలి, నో స్లిప్ బౌండరీ కండిషన్ ఉంది. సో ఈ ఇంటర్ఫేస్ విచ్ ఈస్ ద లిక్విడ్ ఎయిర్ ఇంటర్ఫేస్ దగ్గర డు వీ హ్యావ్ ఎ వాల్? వీ డోంట్ హ్యావ్ ఎ వాల్. అంటే ఏంటి? దిస్ సర్ఫేస్ ఈస్ ఫ్రీ. There is nothing which is restricting the movement of this surface, which means there is no shear stress on this surface. So tau is 0. Shear stress is 0 ante, can you tell me So Newton's law, because if you assume a Newtonian fluid, tau is equal to mu dvy by
du by dy.
du, yeah, same
Mm.
thing, dvy by dx. ఇది జీరో అవ్వాలంటే విస్కాసిటీ జీరో కాదు, విచ్ మీన్స్ dvy by dx is zero. So that's it. We have set up the boundary conditions. What are our two boundary conditions? Boundary condition 1 states at x equal to 0, vy equal to 0. Boundary condition 2 states that at x equal to delta, dvy by dx is equal to 0. ఇప్పుడు ఈ టూ బౌండరీ కండిషన్స్ యూజ్ చేసి the next step would be to solve the problem. So what do you have here? You have d square by dx square is equal to minus rho g by mu, which means vy is equal to, ఇంటిగ్రేట్ చేస్తే మైనస్ రో జీ ఎక్స్ స్క్వేర్ బై 2 mu ప్లస్ c1x ప్లస్ c2. సో 2 times ఇంటిగ్రేట్ చేస్తే we'll end up with this. ఆర్ దీని ముందు స్టెప్లో వీ హ్యావ్ డో vy by dx, అంటే 1 time ఇంటిగ్రేట్ చేస్తే వీ హ్యావ్ మైనస్ రో gx by mu ప్లస్ c1 from here to here and then from అక్కడి నుంచి ఇక్కడికి. But we know that at x equal to 0, vy should be 0. So ఈ ఈక్వేషన్లో x 0 పెడితే ఇది 0 అవుతుంది. We get c2 to be 0. So value of c2 is 0. Now let us look at what is the value of c1. Value of c1 కనుక్కోవాలంటే let us use this equation. We know that at x equal to delta, dvy by dx is 0. So ఈ ఈక్వేషన్లో డెల్టా సబ్స్టిట్యూట్ చేస్తే we'll have c1 to be rho g delta by mu. Now if you know c2 is 0 and you know that c1 is this. So if you use this, we'll get vy is equal to నేను మిస్టేక్ చేశానా? minus rho g x by mu plus c1. Okay, vy is equal to rho g by 2 mu vy is equal to minus rho g x square by 2 mu plus rho g delta x by mu, which is vy is equal to rho g x by mu into delta minus x by 2. This is the equation we are going to have. This is the velocity profile. అర్థమైందా? How these type of problems can be solved? All these arrive from the Navier-Stokes equation. ఈ వెలాసిటీ డిస్ట్రిబ్యూషన్ ఒకసారి చెక్ చేయండి. డస్ దిస్ లుక్ కరెక్ట్ ఆర్ ఎక్కడైనా మిస్టేక్?
అన్నయ్య dvy by dx ఈక్వల్ టు 0 అన్నారు కదా,
అవును.
అంటే ఇప్పుడు VY ని డిఫరెన్షియేట్ చేయాలి కదా అన్నయ్య.
యా ఇప్పుడు Vyని డిఫరెన్షియేట్ చేస్తే మనకి ఏమొస్తుంది? dVy/dx is equal to minus rho g x by mu plus C1. ఇది వచ్చింది. ఇది వచ్చాక నేను x ప్లేస్లో డెల్టా పెడితే dVy/dx should be 0 కదా. సో ఐల్ గెట్ C1 is equal to rho g delta by mu.
ఓకే ఓకే.
సో let us see fluid flow profile ఎలా ఉంటుందో let us try to imagine. So this is the wall. Actually I'll draw it vertical గా గీస్తాను. So I have the wall and I have the free surface. This is the liquid and this is the gas. This is how the velocity profile is going to look. So next thing they have asked us in the question is, so let us check whether this solution is right or not. X 0 పెడితే we need V to be 0, which is being satisfied. X delta పెడితే what are we going to get? You're going to get delta minus delta by 2, which is going to be delta by 2. So we are going to have a maximum velocity somewhere ఇక్కడ maximum అవుతుంది, and then ఇక్కడ it goes కొంచెం decrease అవుతుంది. ఇక్కడ maximum velocity ఉంటుంది. In order to find the maximum velocity ఎక్కడ అక్కడ అవుతుంది, you can find that out by differentiating this. Velocity maximum అంటే ఏంటి? Derivative should be 0. So if you try to differentiate this is a constant, you can ignore it, and you have delta minus x equal to 0, which means x equal to delta దగ్గర, so x equal to delta దగ్గర velocity maximum అవుతుంది. అంటే the velocity profile is going to be this way. ఇక్కడ maximum velocity at the interface, and interface దగ్గర the slope is going to be 0. Slope is going to be 0 because మన కండిషన్ ఏంటి? dVy/dx 0 కదా. సో ఇంటర్ఫేస్ దగ్గర స్లోప్ is going to be 0. అర్థమైందా ప్రాబ్లం ఇప్పటి వరకు? How we calculated the velocity profile and how we can visualize the velocity profile.
Yes అన్న.
And next వాళ్ళు అడుగుతుంది ఏంటి? They are asking us to calculate the flow rate per unit width of the wall. So I will give you a hint and leave this up to you. So flow rate per unit width of the wall అంటే you have your wall and you have the free surface, and ఇప్పుడే కనుక్కున్నాము, we know the fluid velocity is varying in this way. where you have zero velocity here and maximum velocity at the interface. So flow rate, what let us say flow rate ఒక thin element తీసుకోండి. Take a thin element at a distance x and let the thickness of the element be dx. ఈ thickness of the element is dx. And ఈ వాల్ అనేది ఇలా ఉంది. This is the wall. 3-dimensional లో. This is the wall. And the width of the wall is, let us say, w. So if the width of the wall is w and the thickness of this small portion is dx, can you tell me what is the cross-sectional area available for flow for this small element? So if I have a rectangular strip where this length is w and this length is dx, what is the area available for flow?
dx into w.
Exactly. The area is going to be w dx. Now, what is the velocity of fluid through this? What is the volumetric flow rate of fluid through this area? We know that dq is equal to vy times dA, which is vy w dx. This is dq. Now, if you want to find q, you'll have to integrate this vy w dx. Now, you know vy as a function of x మనకు తెలుసు, ఇందాక derive చేసాం. So all you need to do is carry out this integration. Integrate from 0 to delta because x is varying from 0 to delta. So do
ఓకే
this
అన్న.
and నాకు చెప్పండి ఆన్సర్ ఎంత వచ్చిందో చెప్పండి.
ఓకే అన్న.
So one more simple case. Let us say I have a special fluid which is flowing in this way. Perfect flat velocity profile. And the velocity of the fluid everywhere is v. And the thickness is same delta. Can you tell me ఈ కేసులో q ఎంత? What is the value of q?
ఫ్లాట్ సర్ఫేస్ అంటున్నారు కాబట్టి ఆ, మనం ఎలిమెంట్ కన్సిడర్ చేస్తామా అన్నయ్య?
చేయొచ్చు.
ఓకే.
Same procedure, whether అది flat, velocity profile, irrespective of it, you'll go ahead with the same procedure. ఇప్పుడు vy ఏంటి చెప్పు? What is the value of vy?
వివైయా
Yeah.
డెల్టా బై అదే
Any element
ఇట్స్ ఈక్వల్ టు
తీసుకోండి.
డెల్టా.
ఇప్పుడు ఇందాకటి కేసు మనకి vy is equal to some function వచ్చింది కదా, some function of x అని. ఈ కేసులో
ఆ
vy
ఎక్స్
ఏంటి?
లో ఆ ఎక్స్ లో డెల్టా పెట్టాలండి, అప్పుడు డెల్టా బై 2 వస్తుంది.
కాదు. ఇక్కడ నేను ఏం చెప్పాను? ఇట్ ఇస్ అ ఫ్లాట్ వెలాసిటీ ప్రొఫైల్ అని చెప్పాను. అంటే ఏంటి? ఎవ్రీవేర్ ద వెలాసిటీ is కాన్స్టెంట్.
ఓకే.
సో vy is equal to v.
ఓకే.
సో ఇప్పుడు ఈ ఇంటిగ్రల్ లో నేను vy ప్లేస్ లో v సబ్స్టిట్యూట్ చేస్తే v అనేది కాన్స్టెంట్ కదా. సో ఇట్ విల్ కమ్ అవుట్ ఆఫ్ ద ఇంటిగ్రల్ బికాస్ v is no longer a function of x.
ఓకే.
ఇప్పుడు ఇంటిగ్రేషన్ ఏమవుతుంది, Q is nothing but W కాన్స్టెంటే. సో ఆల్ యూ హ్యావ్ ఇస్ VW డెల్టా, అంతే.
ఓకే అన్నయ్య.
That's it. So that's it for today. Thank you everyone. So with this, my fluid mechanics almost cover అయిపోయినట్టే. If there are any topics which you want me to go through again, I'll be happy to do that. Thank you everyone.
ఓకే ఓకే అన్న, థ్యాంక్ యూ వెరీ మచ్. హ్యాపీ బర్త్డే అగైన్ అన్నయ్య. హ్యావ్ ఎ గ్రేట్ డే.
Thank you Shivani.
బాయ్ అన్నయ్య.
Bye.